So we are taking up electric field lines and electric flux today, and when it comes to these electric field lines, they are actually an imaginary concept. There are no real lines as such. Now what these electric field lines really are is that they are a visualization tool. They're a tool we use to visualize electric fields, since electric fields are kind of beyond our everyday life experience, and therefore we kind of invented a tool that helps us visualize these electric lines of force, and that's how we should actually be looking at them. So they are imaginary lines, they're not really there, and also they are a tool with which we try and visualize electric fields. Now what are these lines really? I mean what are they, or how do we imagine these lines? Now these electric field lines are actually imaginary lines. Now they need not be straight, they can be curves, and these are all lines, the tangent to which at any point gives the direction of the electric field at that point. Now as I said, these are lines, the tangent to which at any point gives the direction of the electric field at that point. So that's what these field lines are. Now how do we draw them? Let's take up a simple example of a point positive charge. So if we have a point charge, a positive point charge here, then the electric field lines will be drawn radiating outward from it. So you have electric field lines radiating outward from this positive point charge. At any point on these lines, if I draw a tangent, that tangent gives me the direction of the electric field at that point. Now if in place of a positive point charge we had a negative point charge, lines will be different only to the extent that instead of pointing radially outward, they'll be pointing radially inward. So in this case, the field lines, instead of radiating outward, are radiating inward towards the charged particle. Now if at any point I'm interested in determining the direction of the electric field, then at that point I draw a tangent, and this tangent gives me the direction of the electric field. Now they are the field lines are pointing radially inward, so the field is also pointing radially inward towards the point charge. Whereas with a point positive charge, they were pointing radially outward, and so was the field. Now, one can easily determine one important property of these lines of charge, that as one gets close to a charge, they're more crowded, and as one moves away from the charge, they're that much less crowded. Now, this is actually formalized in physics by saying that the number of field lines passing through an area per unit area in a direction normal to the area is, now actually it's proportional and not really equal, but the way electric field lines are drawn conventionally, we keep it equal. So the number of field lines passing through an area per unit area in a direction normal to the area is equal to the electric field at the location of that small area. Now we have to take a small area because we are assuming that through the area the electric field is constant. So these are the field lines for positive point charge and negative point charge respectively. Now things start to get a little more interesting when we have more than one charge, and we'll take up those cases now. Starting with an electric dipole. So the next charge distribution for which we are drawing field lines is an electric dipole, and we learn something new about these field lines from that example. So let's take up a dipole. Now in a dipole, we have a positive charge, we have a negative charge. The field lines originate at the positive charge and then terminate at the negative charge. Now this is something new for us. This is something that always happens. Electric field lines will always originate at a positive charge and terminate at a negative charge this way. So they're originating at the positive charge, terminating at the negative charge, and they're continuous in between. So we have a continuity with these field lines from the positive charge all the way up to the negative charge. And now if at any point you're interested in figuring out the direction of the electric field, all you do is draw a tangent at that point and you have the direction of the electric field. So the new thing that we have learned about these lines of force from this diagram is that these field lines originate at a positive charge and terminate at a negative charge. When it comes to electric fields that are produced by such static charges, this will always be true. They will always originate at a positive charge and always terminate at a negative charge. They'll be more crowded at locations where electric field has higher intensity, and they'll be less crowded at locations where the electric field has a smaller intensity. Now, another thing that you will always observe about these field lines produced by static charges is that these field lines do not form closed loops. Now, there is a caveat here. There is something you need to be careful about. This is not always the case. In fact, there is no always in science. The electric field lines do not form closed loops when these field lines, these electric fields, are formed by static charges. So when you have electric fields which are formed by static charges, electric field lines will not form closed loops like this. Now, why is that the case? We all know that electric fields are conservative in nature. Electric forces, electrostatic forces produced by static charges, they are conservative in nature, and closed loops would mean that these electric fields are non-conservative. Now, how is that the case? If the electric field lines are like this, and if I place a charge Q over here, the force on the charge would be in this direction, right? And now if I make this charge move along this field line, then the direction of the tiny displacement ds and the force would be same at all points. So you're doing a positive work in every tiny displacement all the way along the loop. So if you start at this point and come back to this point, some positive work would have been done on this point charge. Now, if you start at this point, come back to this point, and some positive work has been done, it would mean that the force or the nature of force is non-conservative. Whereas we are fully aware from our discussions maybe in class 11 when we discussed about nature of forces being conservative and non-conservative, we mentioned electric fields as being conservative. So if you start at this point, come back to this point, there will be positive work, non-zero work. Whereas with conservative forces, the work done in a closed loop should be zero. Since it's not coming out to be zero, it predicts non-conservative forces, non-conservative fields, which is not the case. And therefore, electric field lines cannot form such closed loops. Another property of these lines is that they never intersect. These field lines do not intersect. Now, imagine that there are two field lines and they are intersecting. Then what would happen is that at this point there would be two different directions of the net electric field, which of course is not possible. So these electric field lines generally do not intersect at a point, they do not form closed loops, and there's another interesting pattern that they never really form. I'll be discussing that impossible pattern here. Just have a look. You can never really have field lines which are all parallel to each other but have different densities at different locations. Look at this pattern of field lines. Again, it's not possible to have this kind of a pattern of field lines. They're less dense here and they're getting denser. They're more closely spaced down below, and they're less, the spacing between the lines is larger here, the spacing between them is smaller here. This kind of a pattern is not possible. Now let me explain why that happens. Again, I draw a closed path here, A, B, C and D. And I take a positive charge and I make that positive charge move along this line. Let's say the charge has a magnitude Q. Then the force on the charge here would be in this direction, and we are making it move in the same direction. Now the field here is relatively smaller than the field here. As I mentioned earlier, field lines are closer to each other where fields are larger, and they're further apart where fields are smaller. So the field here is smaller compared to the field here. Now, as we move this charge from A to B, some positive work is done by the electric field, and when we move the charge from B to C, the direction of the displacement and the direction of the force are perpendicular. So from B to C, no work gets done. Then as we move from C to D, we have a larger electric field and therefore a larger force compared to the force here, and the displacements are in the opposite direction. We are moving from C to D, and so some negative work gets done. And then again from D to A, no work gets done because the force and the displacement are perpendicular. So what's happening here, as I start with a positive charge at point A and come back to A, there is some positive work over here, but a small amount of positive work. From B to C, no work gets done. From C to D, some negative work gets done, and from D to A, there is no work that is getting done. So small amount of positive work, let's say for example this small amount of positive work is 50 joule. Then from B to C there is no work. From C to D there is negative work but larger than the amount of work done here. So let's say it is minus 100 joule, and from D to A again there is no work. So 50 joule, 0, minus 100, 0. So if you add them all up, you end up with minus 50 joule. So in a closed loop starting from A all the way back to A, the total amount of work that's getting done is non-zero, which again predicts that this electric field is non-conservative, which is never really the case. If you have electric fields produced by static charges, then they will always be conservative, and this pattern of field lines is therefore an impossible pattern. So we've discussed some properties of these field lines. We've also seen some impossible patterns of electric field lines. Maybe we can have one more example where we have a look at the kind of field lines that are formed. This time, let's say we have two positive charges placed at a small distance from each other. In this case, the field lines will look somewhat like this. Remember, they never intersect. And here we don't really have any negative charges. So there's nowhere in this diagram for these field lines to terminate. And therefore you have field lines just moving away from each other and going all the way up to infinity and finding some negative charge perhaps at infinity and terminating there. So you have these two positive charges. The field here would be in this direction, the field here would be in this direction, and so on and so forth. That's the field line pattern for two positive point charges placed at a small distance from each other. So what we've done now is we've had this brief study of electric field lines. The next thing we are going to do is we are going to define the concept of electrostatic flux, which is again, as it's a continuity. It's a topic related with electric field lines. Essentially, electric flux is defined for an area. We actually, when we define electric flux, we define electric flux through a certain area. So electric flux through an area now electric flux, it's represented by phi. It's a scalar quantity. Now phi, the flux through an area, can be visualized as the number of electric field lines passing through the area. Now, if you recall, the electric field at a certain location is described as the force on a unit positive test charge per unit test charge, and so on and so forth. And also the second thing we have done is we have described the electric lines of force, and these electric field lines, the way we have defined, they are described as being related to electric field in the sense of a density. Now what that really means is that the number of field lines passing through an area per unit area in a direction normal to an area is described as the flux through that area. So what we will do now is we'll consider tiny little areas and try and calculate the number of field lines passing through those areas. Now consider this tiny little area dA. Okay, so we have this sort of tiny area dA, and what we'll also do to make life a little convenient for us is that we'll define an area vector which represents this area. Now, how do we come up with an area vector which represents this area? We'll be defining a vector which we'll call the area vector, and it should have a magnitude equal to the area, and its direction should be normal to or perpendicular to the area. Now at this same location, let's say we have, let's keep things simple to start with, we have an electric field E which is directed normal to the area as well. Now since we have said that at any given location the electric flux through an area is the number of field lines passing through that area, and electric field is number of field lines passing through an area per unit area in a direction normal to the area, which is the case here, it's normal to the area. The number of field lines passing through this particular area, let's say d phi, since it's a small area, the number of field lines will also be small and therefore represented as d phi. This will be E times the magnitude of the area dA. So the number of field lines passing through this area will be equal to number of field lines passing through the area per unit area times the area, right? Very simple. Of course, this was a simple case because the field was perpendicular to the area. As far as the definition of flux goes, the number of field lines passing through an area, this is a simple description. Now, what if the electric field is not normal to the area? Now remember, our description of field lines. When we describe properties of the electric field lines, we said that at any given location, the number of field lines passing through an area per unit area in a direction normal to the area is equal to the electric field intensity at the location of that area. Now, over here, let's say the area vector is in this direction and the electric field intensity is in this direction. And let's say there is an angle theta between these two vectors. Now what we can do is, we'll consider two components of the electric field. One is the component tangential to this area. Now this will be E sine theta, and the other is the component perpendicular to the area, and that is E cos theta. Now due to this E sine theta component, no electric field line is passing through the area, because if a line is tangential to an area, it does not pass through the area. So due to this, no field lines pass through the area, whereas due to this, field lines will indeed pass through the area. So the electric flux through this area now, let's call it d phi, will be E cos theta times the area dA. Now this d phi therefore can be expressed as E dot dA. E dot dA. So we've actually defined electric flux as E dot dA for a small area dA. Now what if we have a larger area? If we have a larger area, then what we do is we divide that large area into tiny areas and calculate flux through all those tiny areas, and then do a summation of flux for all those tiny areas to arrive at the flux through the larger area. Another interesting thing that's done in physics is that the more modern textbooks in physics forget about the number of field lines interpretation and just define flux as this dot product. I don't really see the utility in this. The field lines interpretation works just perfectly and also helps us visualize fields better, and therefore we'll be sticking to the number of field lines interpretation for electric flux. So if you have a tiny little area dA, and that's the area vector, so if my hand represents a small area dA, the area vector would be perpendicular to my hand, and the electric field vector, whatever be its direction, we take the electric field direction, the area vector dA, and look at the angle between them. Take a dot product of electric field vector and the area vector, we get the flux through a small area. Now what if the areas are larger? In case of larger areas, as I have described, we divide the larger area into tiny area elements, calculate the fluxes of those tiny area elements, and then do a summation over those large areas.